Back when we introduced circuit design, we talked about how you can measure certain components of those circuits by using an ammeter to measure the current in series, or by using a voltmeter in parallel to measure the voltage. In this video, we're going to talk about how these meters are themselves not ideal, that by using these measurement tools, we are changing the measurements that we are trying to make by affecting the circuit in other, sometimes unintended ways. This starts out by talking about something called the observer effect. Whenever you take a scientific measurement, there's always a possibility that the act of taking that measurement is changing what you are trying to measure. So, to give a couple examples here, if you're trying to take a pressure measurement on like the pressure of a tire, the act of hooking this up to take the pressure of that changes the volume a little bit of the tire that you're trying to measure. The tool that you're using has a certain volume for that air to expand into, which then reduces the pressure just by taking the pressure. Also, it's impossible to fully seat that pressure gauge sometimes without having some air leak out. So we're trying to figure out the pressure of the tire, but the only way to do that is by changing the pressure of the tire a little bit in the process. This also shows up in other fields that are less concrete. So if you're trying to take someone's blood pressure or take their pulse, a lot of times just the act of knowing that that is happening is enough to change someone's physiological response. That I know for me, whenever a doctor is trying to take my pulse, I'm constantly thinking about the fact that they're taking my pulse and my pulse rises. So they're trying to get my resting heart rate, but what they're capturing isn't really a resting heart rate at all. The act of taking the measurement is changing the thing that you were trying to measure in the first place. Well, this happens for our voltmeters and our ammeters as well. As we talked about before, we're going to describe these in this notation. Basically just a circle with a V or a circle with an A in them. We can draw that on our circuit in the proper location to indicate where we are hooking these up to determine what that voltage and current are. We want to make sure that these tools have the smallest effect on our measurement possible, so that the results that we get are accurate, that using these tools isn't changing the circuit too much that we are trying to measure. So by looking at an ammeter, again, we've talked about ammeters before. Ammeters are always going to be hooked up in series with a component being measured. Basically, to measure the current has to flow through this ammeter. So if I wanted to know the current of going through these resistors, I place the ammeter here. Now, since the current is flowing through that ammeter, we don't want it slowing the current too much. So an ideal ammeter is one that doesn't resist the flow at all, that you can place it anywhere, add a bunch of ammeters, and you're not actually changing the resistance, because an ideal ammeter has a resistance of 0 ohms. Now that doesn't exist. There is no perfectly ideal ammeter, but the goal is to get it as low as possible, because the smaller it is, the less effect it has on the resistance overall, and then the current, again, flowing through. So it's easy to see this in an example. So let's say we have an ideal ammeter. This is similar to what we've looked at before. We've got resistor 1 is 6 ohms, R2 is 2 ohms, and the battery is 12 volts. We want to figure out what the current flowing through this ammeter is. Well, if we know the battery, and we can figure out from our resistances what that total resistance is going to be, this ammeter is not factoring in. That has a 0 ohms because it's an ideal ammeter. So our total resistance in this case is just 6 plus 2. It's just 8 ohms. There is no resistance coming from the ammeter. So if I know R and I know V, I can use Ohm's law to figure out the current coming out of the battery. It's just voltage divided by resistance. 12 divided by 8 is 1.5 amps. That in this case, having that ammeter there didn't affect the circuit's current at all, because that 0 ohms didn't affect the resistance, which then didn't affect the current, 1.5 amps. So what that measured is as if it wasn't there. Now, if this isn't truly ideal, but it's a fairly small resistance, let's give it an example here. Instead of ideal, let's call it a 2 ohm resistor. Now that's probably a little high for what an actual ammeter would be, but just for an illustration here, let's change that to 2 ohms. Now that's going to have a ripple effect on our calculations here, because that changes this from 0 ohms to 2 ohms, which then means that the total resistance is no longer 8. Resistance was 6 plus 2, but now we have to add another 2 because our ammeter has resistance as well. That the total resistance now is 10 ohms. The battery is the same, but our resistance changes from 8 to 10, which means our current, which was 1.5 before we added this ammeter or gave it some resistance, is now going to be 1.2. That this ammeter affected the measurement it was reading. The current, instead of being 1.5, is measuring now 1.2. This non-ideal ammeter's resistance is slowed down that current, so it's reading something slower, a lower current, than it actually was if it was not affecting the circuit at all. Let's flip gears and talk about what this means for a voltmeter. A voltmeter, again, is hooked up in parallel with a component being measured. If I wanted to know the potential difference that is across this resistor, I basically connect 2 leads, one on either side of the resistor, for my voltmeters, measuring the difference from one side to the other side of that resistor. Now, we don't want this affecting the circuit much at all, just like we didn't want the ammeter to affect it. And here, this is adding a parallel branch. It would change the circuit dramatically if a lot of current started flowing through that branch as well. That now we have 2 pathways for current to flow, and it's no longer the circuit we were trying to measure. We want this thing to be essentially invisible. So the way to do that is by increasing its resistance so much that the current can't flow through there. It's just looking, the current isn't actually flowing through, and the highest resistance we could have is infinity ohms. Obviously, there is no such thing as infinity ohms. There are a lot of things that have a low resistance, or a very, very high resistance, low conductivity, but infinity ohms is our ideal. So let's look at what happens with an ideal versus non-ideal voltmeter. Say we have the same circuit that we had before, 6 ohms and 2 ohms with a 12 volt battery. I want to know the reading for this ideal voltmeter across resistor 1. Now this process is a little bit more involved than when we talked about a non-ideal ammeter. To find the ideal, this voltmeter reading here, I first need to figure out some other things about this circuit. I know that this voltmeter is going to be ideal, so it's infinity ohms. So if I wanted to figure out from this what the equivalent resistance is, I can find a total resistance of this parallel branch, which looks kind of silly, but it's 1 over 6 plus 1 over infinity, because this is technically a resistor in this form, and it has a lot of resistance. Now that is connected in series with this 2 ohm resistor, so I'll just add that 2. Now I can simplify this down because 1 over infinity is essentially 0. If you're dividing by the biggest number possible, you don't have anything there. So we're just going to ignore that right now. So that turns into 1 over 6, which is the same thing as just saying 6. And what this means is basically it makes this invisible, that this is operating just as a series circuit, the 6 ohms plus 2 ohms to get our equivalent resistance of 8 ohms. So just a fancy way that's going to help us in the future here of showing that we didn't have to worry about this infinity ohm ammeter or voltmeter. It was essentially invisible to the circuit. So then if we know that the total resistance is 8 ohms, we can find the current flowing out of the battery. Just voltage divided by resistance, 12 divided by 8 is 1.5 amps. That is the current that flows through R2 here. So I can figure out what the voltage drop of R2 would be. That would be V is I times R. 1.5 times 2 is a voltage drop of 3 volts. Now I can think of this loop here with Kirchhoff's loop rule, saying that the voltage provided has to equal the voltage dissipated within this loop. Again, this loop now totally ignores the voltmeter. I don't have to worry about the voltmeter. All I have are R2 and R1 that have to totally dissipate the 12 volts that are provided. Well, 3 volts is dissipated by our V2, so R2 here, which means that all that's left over is 12 minus 3, or 9 volts. If this R1 has 9 volts, that's what the voltmeter reads. It reads the voltage of R1. So all of that process to get us to a final volt reading of 9 volts. Again, we found the equivalent resistance, use the resistance to find the current, use the current to figure out the voltage drop in R2, and then use the loop rule to figure out what was left for R1. Now, not every voltmeter is going to be ideal. If we have a voltmeter that is not ideal, it's going to have a larger voltage or a larger resistance, but not infinity. So let's say it's a 12 ohm voltmeter. That turns this obviously not infinity anymore. That's now 12 volts or 12 ohms. This also then ripples into my equation for the total resistance here. Instead of infinity, this is 12. So I can't just turn that into a 0 anymore, that this 6 becomes 4. A 12 and a 6 ohm resistor in parallel with each other turns into 4. You could do that on your calculator. 6 to the minus 1 plus 4 to the minus 1, all that to the minus 1 will give you 4. Now 4 plus 2 is 6. You can see how this is kind of trickling through, that this parallel branch is 4 plus 2. Now the overall is 6, which means that affects my overall current is now 2 amps instead of 1.5, which means that the voltage drop in R2 instead of 3 is now 4 volts, which means that there isn't as much voltage left over for R1. So that turns into 8 volts. So a long walk to get there, but what we see here is the voltmeter. We are trying to measure the voltage across R1, and we know that without the voltmeter there, it was 9 volts. The voltmeter didn't affect it in that first calculation, but because the voltmeter was not ideal, it actually dropped the voltage that it read because it made this equivalent resistance a little bit lower than it was before. So to see this in another way, we can look at this in kind of a backwards fashion. So say we hook up this ammeter and it reads 1.2 amps. That is enough information to actually tell us what its resistance is. So if we know everything else about this circuit, we can figure out, okay, if that resistance is 1.2 amps, or sorry, that current is 1.2 amps, that current is the same for all components. That's what's flowing through A, but since this is in series, all of them are receiving that 1.2 amps. So I can calculate the total resistance if that's the current coming out of the battery, and I know the battery voltage is 12. Resistance is just voltage divided by current. So that's 12 divided by 1.2. That total resistance has to be 10 ohms. Well, I have resistances here for R1 and R2 that if the total is 10 ohms, I can figure out what that ammeter has to be so that all of these add up to 10, because I notice that this 3 ohm and this 6.5 don't add up to 10. There must be some resistance left here for this ammeter. Adding those together, requiring to get to 10, means that that ammeter must be providing half an ohm of resistance. So 0.5 ohms of resistance there for our ammeter. If we look at an example of a voltmeter, say we connect it up to this circuit here, we see that our voltmeter reading is 7 volts. Again, this is going to be a little bit longer walk to get to where we need, but we can calculate the resistance of this non-ideal meter just with the fact that it's measuring 7 volts. Because if it wasn't there, this wouldn't actually be measuring 7 volts. Instead, it'd be measuring something a little bit higher. So a couple steps to get there. We're going to use voltage loops to calculate the voltage drop for R1 and R2. Well, we see that this ammeter is measuring 7 volts. So we know that R1 has a voltage drop of 7 volts. That's what the voltmeter is actually measuring. R2 is going to be whatever is left if our total voltage provided is 12 volts minus 7 volts leaves us with 5 volts overall. These two resistors in this loop add up with a voltage dissipated to equal the voltage provided of 12 volts. Now my next step is to calculate then the current that is flowing through R1 and R2. If we know 2 of the 3 main electrical properties, we can calculate the third. Finding the current is just voltage divided by resistance. 7 divided by 4 is 1.75 amps. 5 divided by 2.5 is 2 amps. So then I can look at a current junction here right at this point where it splits off into the voltmeter. I know that this current isn't exactly the same, that it lost some of its current some of it is flowing through this voltmeter. I can look at this junction to figure out how much. 2 amps becomes 1.75 amps, which means that there has to be 0.25 amps, a quarter of an amp, going up to this branch towards that voltmeter. All right, that's going to be useful for us because if we know the voltmeter is measuring 7 volts, that's the voltage it has over it. We've got a current going through of 0.25. We now have enough to find the resistance. Voltage divided by current, 7 divided by 0.25, gives us a resistance for that voltmeter of 28 ohms. Again, it's higher, which is good, but it's not infinity, so it is not ideal for that voltmeter. Some of that current is still flowing through it. So some takeaways here. You should be able to know how to connect a meter to measure current or voltage. Know, is it in series or is it in parallel? Describe the conditions required for an ideal ammeter or voltmeter. An ammeter should be an ideal 0 ohms. Voltmeter should have an ideal of infinite ohms so that nothing flows through it. And then you should be able to calculate a situation when the meter isn't ideal. We went through 4 different examples, 2 of each. It might be worth rewatching some of those because they're a little bit more challenging to follow all the way through to the end.